Moving along on our trigonometric journey, there are certain ratios that are of interest to us. In fact, they're related to certain angles as well. Let's try a few. For example, why does sine of 30 degrees equals 1 on 2? In fact, if you try that for yourself, you end up with half. Okay, that's a very interesting one, because if you try anything else, so for example sine 31, move along from half, you go slightly above 0.5, and for example sine of 29 degrees is slightly below 0.5. So what's going on here? What about tan of 60? Okay, now I've kind of given you the answer already. If you were to type in tan of 60 into your calculator, you get 1.73205. Square root of 3 is exactly the same. So again, what's going on here? You know, tan, the tan ratio is opposite over adjacent. So what's this telling me? Root 3. Opposite over adjacent is equal to root 3. What about, say, the cosine of 45 degrees, cos of 45? Okay, so cos of 45. 0.7071, and in the topic of surds, we did look at this. This value did come up actually when we looked at rationalizing denominators. In fact, 1 divided by square root of 2, 0.707. In fact, there was one of the videos that I'd done, and I did this as an example, and we rationalized the denominator for 1 over root 2. It's the same as root 2 divided by 2. 0.707. Again, what is going on here though? And that's really the question, isn't it? In fact, try one other one. For example, let's say tan of 45 degrees. I like this one. 1. Wow, that's a nice ratio. Opposite over adjacent equals 1. What kind of a triangle has that? Where the opposite side and the adjacent side, you divide one by the other, you get 1. What does that tell you about the opposite side and the adjacent side of that particular triangle? Anyways, we'll look at that later on. So there are certain angles that result in exact trigonometric ratios. Okay, and I've summarized them here in a table. So in the first row of the table is the angle. Okay, so the angle this is in a right angle triangle, by the way. So if you have, I might just sort of sketch one. Okay. So this is our angle theta there. Okay, there's our right angle triangle. Okay, and for example, you took the sine of 0 degrees. That's opposite over hypotenuse. You get 0. Okay. When theta is 0 degrees, the hypotenuse, in fact, falls on the adjacent side. The opposite side is actually 0 in length. And 0 over the hypotenuse is just 0. Sine of 30 degrees equals 1 on 2. So that would mean then that the opposite side would be 1. The hypotenuse would be 2. Same thing with sine of 45 degrees. Opposite side is 1. The hypotenuse is square root of 2. Sine of 60 degrees, root 3 on 2. Okay, so root 3 over 2. Sine of 90 degrees is equal to 1. Okay, so when theta is 90, okay, so that way, the hypotenuse and the opposite side are in fact equal in length. So you'd get 1. Now look at the cosine ratio, the cosine trigonometric ratio. What do you notice about sine of theta and cosine of theta? Look at the values carefully. In fact, if you took sine, flipped it around, you get cosine. After all, isn't sine and cosine complementary to each other? In fact, isn't that what cos stands for? Stands for complement of sine. So in other words, cos of 30 degrees is exactly the same as sine of 60 degrees, root 3 on 2. Okay, cos of 60 degrees is the same as sine of 30 degrees. Cos of 90 degrees is the same as sine of 0 degrees. So cosine basically is just sine, but just back to front, purely because of its complementary relationship with sine. Okay, remember, sine of, for example, sine of 30 degrees is equal to cos of 90 minus 30 degrees, which is then equal to half. And lastly, the tan ratio. Okay, so tan is equal to sine divided by cos. So in actual fact, the last row you can derive by dividing sine by cos. So 0 divided by 1 gives you 0. 1/2 divided by root 3 on 2 gives you 1 divided by root 3. Okay, so I might just do that here just so you can see what I mean. Okay, so 1/2 divided by root 3 on 2, okay, is equal to 1/2 multiplied by 2 over root 3. Okay, the 2's cancel and you end up with 1 over root 3. Okay, so, and the same for the rest of them. 1 on root 2 divided by 1 on root 2 gives you 1. And again, that's another reason why tan of 45 degrees equals 1. Tan of 60 degrees, root 3. Root 3 on 2 divided by half is the same as multiplying it by 2. Root 3 on 2 multiplied by 2 equals root 3. Now, tan of 90 degrees is a very interesting one. In fact, when we come to graphing these functions, yes, you can graph sine, cosine, and tangent functions, of course. Tan of 90 degrees gives you a math error. In fact, this is partly the reason why anyway, but one reason why it gives you a math error is if you look at the definition of tangent as sine divided by cos, you have 1 divided by 0. Now, UND means undefined. It means we don't know what it is. It could be infinity, it could be negative infinity. I mean, it could be anything. I mean, but generally we either put the answer as plus or minus infinity as well as you can say undefined, because it's not defined. We don't know what the value is. So it's some humongous number. We don't know. Let's have a look at the proof of these ratios. Okay, and the proof really comes from, or the origin really of these ratios really comes from two very special triangles. Remember that question I asked you about why is tan of 45 degrees equals to 1? And I said opposite over adjacent is equal to 1, 1 over 1. That's an isosceles triangle. That's this triangle here. But let's start with this one first, the equilateral triangle. So what I've drawn here is an equilateral triangle, side length of 2. 2, 2, 2. So the bottom, what I've done is I've divided the equilateral triangle in half. So I drew a perpendicular. So from the midway point, all right, to the apex of the equilateral triangle, that means that the equilateral triangle, I've divided it in half. We can use congruent triangles, theorems to prove that, this triangle is equal to this triangle, or congruent to this triangle. I'm not going to bother. You can do that for yourself. Okay, so that would be the side. You could use side angle side, to sort of prove that these are in fact equal to each other, and therefore this and this side here and this side here are in fact equal. The bases are split. The base is split perfectly in half. Great. However, because now we've got two right angle triangles, we can focus on one. We need the height of this equilateral triangle. Okay, and the height of the equilateral triangle can be found from Pythagoras' theorem. So that's just 2 squared minus 1 squared, first of all. Okay, so that's 4 minus 1, all right? So that's equal to square root of, so 4 minus 1 is 3. And so that's the height of this equilateral triangle. Now, sine of 60 degrees, okay, is equal to root 3 on 2. All right. And if you look at the table that we drew up before, okay, sine of 60 degrees, root 3 on 2. And that's where that comes from. Okay. Keep going. What about cos of 60 degrees? Cos of 60 degrees is 1 over 2. It's half. Okay, what about tan of 60 degrees? Okay, tan of 60 degrees. Opposite over adjacent. Root 3 over 1. Okay, and that's equal to square root of 3. What about, let's say we haven't done 30 degrees. In fact, if you now switch the angle or change the angle from 60 to 30, okay, sine of 30 degrees is equal to opposite, which is now the 1, over the hypotenuse, and there's half. Cos of 30 degrees, okay, is adjacent over hypotenuse is root 3 over 2, and tan of 30 degrees, okay, is equal to opposite over adjacent. So 1 over root 3. Okay, so we've seen those in the table. Let's have a look now at the isosceles triangle. So this is the triangle where the angles other than the 90 degree are 45 degrees each. And I've made the side lengths, just for convenience, 1 unit. Okay, you can make them whatever you like, as long as they're equal. After all, opposite over adjacent equals 1. We saw that. This is the reason why. They've got to be equal in length. So let's just make them 1. Just nice and easy. Now, being an isosceles triangle, we can use Pythagoras' theorem as well, because it's not only isosceles, it's also a right angle triangle. X is equal to the square root of 1 squared plus 1 squared, which is equal to root 2. Okay. Now, sine of 45 degrees is equal to 1 over root 2. And if we rationalize that, okay, so if you want to multiply that by root 2 on root 2, okay, is the same as root 2 over 2. So you might have seen either this value or this value in that table, or in one of those tables of exact ratios. Cos of 45 degrees, same thing, switch angles. Okay, but because it's an isosceles triangle, the opposite and the adjacent are in fact equal anyway. So it's 1 over root 2 yet again. Okay, what about tan 45 degrees? Okay, we know the answer is going to be 1. It's just 1 over 1, and the answer is 1. And that's the origin of the exact trigonometric ratios. Now, in a subsequent video, there's one last thing I just want to quickly show you, and that is if you took, for example, let's say sine of 150 degrees. It's also half. Okay. What about, say, tan, I think 240 degrees? Square root of 3. But you might think, hang on a moment, how do I have a triangle with an angle inside it that's 240 degrees? Isn't the angle sum of a triangle 180? Where does this... Anyways, that question will be answered later, okay? But interesting to note that there are other angles that also give us these exact ratios as well. Thank you for watching, everyone.